I just created a standing wave on the college guitar here, and it's come out, of course, with a certain frequency. Another standing wave. Well, it's interesting when we look at these instruments to analyse what frequency, velocity, wavelength all depend on. Of course, in the case of guitar, this length here is half a wavelength. And what we've got is a standing wave. We've got a wave which goes in this direction and in that direction added together. And this, of course, is what produces standing waves. Of course, this wave has a velocity along the string. And what we're going to do is explore some of the factors which affect that velocity. One of them is what's called linear density. Now this one here is made out of metal. It has a higher linear density than this one down here, which is made out of nylon or plastic. What that linear density means is how much mass per unit length. And we measure linear density in kilograms per metre. Kilograms per metre of string. Another thing which affects the frequency and the velocity of the waves in this musical instrument is the tension here. We can adjust the tension or the force being applied to the string. And we're going to explore those using some slightly different equipment. So this is the equipment that we're going to use to explore the standing waves, and what I'm going to do is follow through the instructions that you've got in your workbook. And it's to deal with practical 3, and it's round about page 28, if perhaps a little bit more or a little bit less. But let's look at what it says. In this experiment, a string has one end connected to a mass hanging over a pulley to give it tension. Now this is what we've got here. Here's our mass down there, and we're calling that a pulley. It's a smooth surface so that there's very, very little friction that's going to take effect. The other end of the string is connected to a vibration generator, which in turn is connected to a computer via a data logger. So this is our vibration generator here. Here is our data logger, and it's connected to the computer here. The vibration generator creates a series of pulses, that is a wave that passes along the string. The wave is then reflected from the other end and interferes with the original wave. The wave is then reflected from the other end and interferes with the original wave to create a standing wave. Now the velocity of the wave in the string is given by the formula V for velocity is equal to the square root of the tension divided by mu, which is the linear density. Now the linear density, as we've seen before, is worked out by getting the mass and dividing that by the length. Now it says the linear density is a constant for any one type of string. The linear density is independent of the length. More accurate measurement of mu can be found by using a longer length of string. Why is this the case? Well, first of all, the long length of string that I used was 16.2 meters. Now that figure needs to go into your workbook here, where it says length of string, meters. Now the mass also needs to go into that table on page 31 or thereabouts, where you are recording your results. And the mass of the string was 20.29 grams. That will enable you to work out the linear density, which is in the next row of the table. You will simply divide those, the length into the mass to get the linear density. Now, going back to the previous page, page 28 perhaps. The wavelength lambda of the standing wave can be found by counting the number of nodes and antinodes. So the number of antinodes, areas of maximum displacement, that will give us the number of half wavelengths. So the frequency can be found from the data logger, and the velocity can be calculated using this formula of V is equal to the square root of T divided by mu. So we've got two parts of this experiment. First of all, a look at 5 harmonics. And it says, in this experiment you will measure the frequencies of the first 5 harmonics for a stretched string of a constant length. You will then draw a graph of wavelength against frequency and see if you can work out which variable you can manipulate or change, in other words, to produce a straight line. From your straight line, you need to measure the gradient. Write the full equation for the graph and explain the significance of the gradient. So, let's have a look at the aim. What are we trying to do? We're trying to find the relationship between wavelength and frequency. So the next section is the theory section, and what you're looking at there is what do you expect to happen. So it asks you to work out the wavelength and the frequency of the various harmonics. So you can do that from the few pages that are previous to this experiment. So let's look at where we're up to at the moment. We've got our table of results. We've got the mass of the string, we've got the length of the string, so that's the large length, and that's enabling you to calculate the linear density. We next want to have a look at the length of the vibrating section of the string. So what that means is this length here. So I'm going to get the rulers that I need and work this out, and what I'm going to find, because I did this a little bit more carefully earlier on, is that length is 110 centimetres. So you need to write that in the next row of the table where it says length of vibrating section of the string in brackets m. So convert that 110 centimetres to metres. So the mass here is 150 grams. So we can write that figure in the next column of the table. Then it says the tension in the string. Well, that tension results from gravity acting on that mass. So the tension or force is mg. And what you need to do is change the grams into kilograms and multiply by 9.8, and that will give you the tension in newtons. From that you can calculate the velocity that we expect to get from this experiment. You know the tension, capital T, and you know the linear density. So you can get the square root of that ratio and write that in. So the next section is to look at the harmonics. The first harmonic is half a wavelength. So what we're going to do is look at our computer over here, and to begin with we need to tell the computer that we're going to use the signal generator. So I'll click on signal generator, and this one here happens to be 550 output, which doesn't matter. And what we're going to do is adjust the frequency that the generator produces to get our string here vibrating in the first harmonic. Now, the first harmonic, as you may already know, is also known as the fundamental. It's the lowest vibration which can fit in. So I'm going to adjust the amplitude. I'm going to adjust the amplitude to maximum, up there to 8, and I'm going to reduce the frequency here to something small to start off with, maybe 10 hertz, 10 vibrations per second. And I'll click the on button then, and we can see now that the string is vibrating. At the moment, the string is not vibrating in the fundamental mode, so what I'm going to do is change the frequency. I'm going to increase the frequency, so it's now 11, 12, 13, 14, 15, 16, 17. Now that is getting closer to looking like the first harmonic. I'll just raise it a little to 18. See if it gets better. No, that looks worse. So I'm going to take it back down to 17. See if it settles nicely at 17. No, that doesn't look very nice. So I'm going to lower it down a little further, 16. Okay, so 16 there looks like a nice vibration. So I need to, or you need to write that down into the table of results underneath where it says 1. Measured frequency from the data logger. Underneath 1, you need to write 16. That's for the first harmonic. Let's go now to the second harmonic. So I'm going to increase the frequency. So 19, 20, 21, 22, 23, until I get the second harmonic, a nice pattern. That looks okay. Maybe it's better if I raise it up a little. 30 at the moment, 31, 32. I'll try 33. 33 looks all right. Looks even better. 34. Well, now it's starting to play about a bit, so I'm going to take it down. 33. That looks quite nice. No, it's become unstable. That's somewhere between 33 and 32. There's 32. I'm going to settle on 32, so what I'd like you to do is to write 32 underneath the number 2 for the second harmonic. Let's then go to the third harmonic. Now I can see almost see 3 half wavelengths there. And see, I'm up to 45, 46. See if I can get a better, more stable pattern. Okay, that looks even better. That's 48. So I'll raise it to 49. No. Okay, so I'm going to take it back down. 48. I'm going to settle on 48 then for the third harmonic. So in your table where it says measured frequency, underneath the letters, underneath the number 3, type in or write in 48. I'll boost the numbers again. I'll boost the frequency again. So it's 55, and it looks like something's emerging there. 58, 59, 60, 61, 62, it's getting better actually, 63, better still, 64, I'll try 65, that looks alright, I'll try 66, see if it gets better. No, I think that's worse, so I'll take it back down again to 65. Wasn't as good as it was before. 64. I think I'll settle on 64. So underneath 4, please record 64. Now I'll increase the frequency again, see if we can get the frequency that brings us the 5th harmonic. We're getting close to it now. I've got 74 there, 75, 76, 77, 78, 79, 80, 81, 82. 82 threw it out, so I'm going to take it back down. 81, 79, 78, 76, 75, 76. That's 80 now. I'll just try up to 81. That's 81. 82. No. So I'm going to stop now, turn this off. Let's look at our table now. We've got to work out the wavelengths of the number of nodes and antinodes. So remember, the first one was 110 centimeters, so that was for half a wavelength. Okay? That length was half a wavelength for the first wavelength. So our wavelength for, or lambda, for the first harmonic is twice that, 210, in other words 2.20 meters. For the wavelength for the second harmonic, well, that was that length itself, so that was 1.10. The third harmonic, you can work that out, that's going to be 2/3 of 110, or 2/3 of 1.10 meters. And similarly, you can work out values for the fourth and fifth wavelengths. The next thing that we need to do is to hand draw, or better still, use Excel to plot a graph for the measured frequency from the data logger versus the wavelength. The wavelength is calculated from the number of nodes. Well, we've already done that. So let's draw this graph. Now to graph the frequency against 1 over the wavelength, what I will do is just make a copy of this particular column, place it on this side, and expand our column there, and click this, hit the escape key to remove the crawling ants around that. And now I'll select these values and go up here to insert, down here to create a graph, click there, and that gives me the second graph, which I'll put down here, and or in such a position that can be seen. So there it is there. So there it is there. What I'm going to do now is add the chart title and the labels and the units. So with the graph drawn, I'll just select it and put on a line of best fit. I'll go up here to trend line to put in a line of best fit. Click that. I'll go to more options and click ensure that linear is selected because it does look like a straight line, and then I'll set the intercept to 0. That will make the line effectively pass through 0, and click display equation on the chart. I can now close this, and this is my result. And what I've got here is the gradient. Now let's see what the gradient represents. So getting the gradient, of course, means getting the rise over the run. And as you know from your mathematics and the equation for a straight line, in this particular case, it's going to be getting the frequency divided by 1 over the wavelength. And when we do that, of course, we get frequency times wavelength, and that is frequency times lambda, or f times lambda, and this then is our equation, or more accurately, we should say the velocity is equal to frequency times the wavelength. So this is what we've done in this experiment. We've been able to calculate the velocity simply by looking at those that relationship between frequency and wavelength. So looking at this question, how does your gradient compare with the calculated value? Explain any differences. Well, you've seen from the calculated value, that's 35.2. You've calculated the value from the experiment. How do they compare? First of all, you should say, are they the same or are they different? Now, if you think they are different, then what are some of the things, some of the measurements that were made during the experiment? What can you think of in terms of the measurements that were made during the experiment that could lead to a difference in those velocities, those calculated and experimental values for the velocity? One thing to keep in mind is the point at which the frequency generator goes up and down is not exactly a node, okay, because it is moving. I would suggest that the wavelengths might be slightly longer. Looking at number 4, write a full equation. Well, we've got that written there, as you can see. So this is the equation that we've come up with. Y, of course, though, is the frequency, and x is 1 over the wavelength. So in writing a conclusion, let's have a look at what you need to say. First of all, what you did in the experiment. For that one, say something about keeping the tension constant and the linear density of the string constant while you change the frequency to see how the wavelength changed. That's what we did. For the second one, the calculated value of the velocity, all you need to do here is state the theoretical value, the one that we worked out from that formula. The C, the conclusions from the graph. Well, again, here, just write something about the mathematical relationship that we found between the frequency and the reciprocal of the wavelength. For D, the velocity of the wave found using the graph, all you need to do here is state the velocity from the graph. For E, comparing the two velocities, just say very briefly whether or not you thought they were the same. After this, we can look forward to doing the second phase of this experiment.